Module 2, Lecture B, Dictionaries and Sets. By the end of this lecture, you will be able to build dictionaries that associate engineering identifiers with relevant values, use sets to identify unique items and compare collections of resources, and combine built-in structures to represent small industrial engineering datasets. Key value maps. Machine identifier maps. In engineering settings, a dictionary links each unique machine identifier, such as a serial number or asset tag, to details about that machine, like its status or location. The identifier is the key, and the machine information is the value. This makes it easier to tell similar machines apart and quickly find the exact record needed without searching through long reports. Machine identifier maps help manufacturers track key information for each piece of equipment, such as its department, energy rating, service schedule, and current status. By linking each unique machine identifier to this data, teams can quickly check whether equipment is active, under maintenance, or due for service. This makes reporting, troubleshooting, and record-keeping faster and more consistent. A reliable machine identifier map gives each machine a unique name, preventing confusion in logs, data, and system records. Consistent naming conventions, often based on location or machine type, help teams avoid misidentification. Clear identifiers make it easier to organize information, connect observations to the right records, and support sound engineering decisions. Python code, machine identifier maps. Dictionaries link equipment identifiers to useful machine information. Each key should uniquely name a physical device, while each value stores relevant engineering status details. Create a dictionary to track machine status by linking each machine's unique identifier to its current state, such as active or idle. This makes it easy to monitor and manage the operating condition of multiple machines in a system. This code defines a dictionary for tracking machine status. It records that LN2 Robot 1 is under maintenance and Util Pump 3 is out of service, giving a simple, structured view of which machines are not currently operating normally. A specific machine, LN2 Robot 1, is selected, so its current status can be looked up in the Machine Status Dictionary. The retrieved value is stored for easy reference to that machine's operational state. We add a new machine status entry for the quality control camera, identified as QC Camera 2. Its status is set to active, meaning the camera is currently operational. This expands the dictionary so the system can track this additional piece of equipment. The machine identified as Util Pump 3 is being updated from out of service to under maintenance. This shows that it is no longer simply unavailable, but is now being repaired or checked. Keeping this status accurate helps track and manage equipment effectively. To find the distinct machine status labels, convert the status values into a set. This removes duplicates automatically, leaving only the unique statuses across all machines. The output reports key information about the selected machine and the overall machine list. It shows the selected machine's identifier and current status, then displays how many machines are being tracked. It also lists the distinct statuses across all machines by removing duplicates and sorting the results for readability. This code goes through each machine entry in the status dictionary and retrieves its identifier and current status. It then prints them together in a simple format, making it easy to review the state of every machine. The script uses a dictionary to track machine identifiers and their current statuses, such as active, idle, under maintenance, or out of service. It retrieves one machine's status, adds a new machine, and updates another after maintenance. It also finds the set of unique statuses, reports the total number of tracked machines, and prints each machine with its current status for a complete overview. Part values. In engineering, dictionaries are useful for connecting stable identifiers, such as part numbers or serial codes, to key information like cost, material, specifications, or inventory status. This gives engineers and technicians a fast way to find the details they need without searching through long documents. It reflects how industrial data is often organized, where each part label points to the information needed for operations and decisions. When building a dictionary for part data, define it around the question it must answer. A production cost dictionary might connect part identifiers to prices or processing times, while warehouse or quality tasks would use inventory, location, inspection status, or approval dates. Keeping the values focused makes the dictionary efficient, clear, and aligned with the engineering need. In engineering, dictionaries for part value maps help keep data names and values consistent. Identifiers should be clear, distinct, and predictable, and values must show their meaning reliably, such as whether inventory counts are estimated or verified. This consistency makes dictionaries dependable links between design data, production planning, and operations, reducing mistakes like ordering delays or assembly errors. Python code, part values. Dictionaries link identifiers to useful engineering values. For example, part numbers can serve as dependable keys, with each value providing the answer to one specific operational question. Create a dictionary that links each part number to its unit cost in US dollars. This provides a quick way to look up costs by part identifier, supporting efficient inventory management and pricing calculations. The dictionary adds unit costs for two more parts. Plate 330 costs $31.10, and Seal 415 costs $6.40. With these entries complete, the dictionary can quickly look up each part's cost by its identifier. A specific part, identified as shaft 204, is used as a key to look up its cost in a dictionary of part costs. The retrieved value is stored as the selected cost, making it easy to use that part's cost later in the program. To safely look up a dictionary item that may be missing, use the GET method with a default response. In this example, the program searches for a suspected missing part and provides a fallback message if no cost is found. This prevents errors and lets the program handle missing data gracefully. A new dictionary entry is added for part number PIN 502 with a unit cost of $3.85. Then the dictionary's length is used to find how many unique parts are currently being tracked. To find an order's total cost, store each part's ordered quantity in a dictionary. Then use the sum function to add the cost for every part by multiplying its unit cost by the quantity ordered. The result is the total cost of the order. The example prints key results from a parts dictionary. The cost of shaft 204 formatted to 2 decimal places, a fallback message for the missing part bolt 999, and the total number of tracked part identifiers. It then calculates a small order total by multiplying each part's unit cost by its quantity, and prints the final cost with 2 decimal places. The script uses a dictionary to track part costs by part number. It finds the price of shaft 204, reports a fallback message for a missing bolt, and adds a new pin to bring the tracked parts to 5. It then calculates a small order total from item quantities and unit costs, producing a final total of $174. Dictionary lookups. Dictionary lookups make key value maps useful by letting you retrieve a value directly from its key. In engineering or industrial data, a machine tag can quickly lead to information like maintenance status or calibration dates. A well-chosen key acts as a reliable index, helping you find the right information efficiently in large datasets. Dictionary lookups depend on consistent identifiers. If the same motor is named in different ways across records, the system treats each name as a separate key unless they are standardized. This is why engineering systems rely on strict naming conventions and high data quality. A lookup only succeeds when the search key exactly matches the stored key. Dictionary lookups organize engineering data by connecting each identifier to the information it represents. This lets users quickly retrieve details such as inspection dates, production targets, or tolerance limits through a consistent key and value pattern. Even as datasets become more complex, the basic purpose stays the same, turning identifiers into useful information for software development, process analysis, and decision-making. Python code, dictionary lookups. Dictionaries link identifiers to their stored values, and lookups find those values only when the exact key is used. Using consistent engineering identifiers is essential to avoid lookup failures. A machine status dictionary maps each machine identifier to its current operating state. For example, one machine may be marked for scheduled maintenance, while another is running normally. This makes it easy to look up any machine's status using its identifier. This code adds a new machine status entry for pump P104, marking it as needing a vibration check. Storing this information in a dictionary makes it easy to look up and manage each machine's operational status by its identifier. To check a machine's status, use its exact name as the key in the dictionary. Looking up press line 3 or pump P104 returns the current conditions stored for that machine. These direct key-based lookups provide precise information as long as the key matches exactly. Use the dictionary get method to handle missing keys safely. When retrieving a machine status, it can return a default message such as identifier not found if the requested motor is absent, instead of raising an error. This keeps the program from crashing and gives a clear fallback response. The code looks up machine statuses in a dictionary and prints the results. It successfully reports the statuses for press line 3 and pump P104, then tries to look up motor 17. Because that identifier is missing, the get method returns the default message, identifier not found, so the program continues without an error. A dictionary is used to store each machine's hourly production capacity in metric units. It links machine names, such as press line 3 or robot arm A2, to their output rates, making the values easy to look up for planning and calculations. Pump P104 is assigned an hourly capacity of 40 units. This value represents its production rate and is used in planning and operations to allocate resources based on the pump's output capability. The process selects robot arm A2 as the machine for the planning calculation, then looks up its hourly capacity in the capacity data. The retrieved value is stored for later use in calculations or reports. The code displays the production capacity of the chosen machine. It looks up that machine's hourly capacity from a dictionary, then prints a clear message with the machine name, its capacity value, and the units per hour. This example shows how Python dictionaries can quickly retrieve machine information using identifiers as keys. It looks up machine statuses, uses a safer lookup that returns a default message when an identifier is missing and retrieves a machine's hourly capacity from another dictionary. The main idea is that dictionaries provide efficient access to stored data while helping handle missing entries cleanly. Unique resource sets. Set basics. A set is a data structure that stores only unique items, so duplicates are automatically removed. This is useful in engineering data, where the same record may appear more than once, such as repeated pump entries in a maintenance log or repeated workstation identifiers in manufacturing data. By focusing on distinct items, sets make summaries clearer and help avoid double counting. A set is defined by whether an item belongs to it, not by order or repeated entries. Adding the same item again does not change the set, because membership is unique. This makes sets useful for organizing resources such as machines, tools, or certifications, and for answering practical questions about capabilities or component use. Sets help turn raw data into meaningful summaries by keeping only unique items and removing repetition. In operations, they can show which pallets, products, or dock doors were involved without extra noise. This makes records easier to compare, audit, and use for planning. Python code. Set basics. Sets store unique engineering resource identifiers by combining repeated observations into a single membership list. This makes it easy to check whether a resource is included. We create a list of workstation scans that includes repeated observations of workstation identifiers, such as CUT1 and WELD2. This simulates seeing the same workstation multiple times, so the data can later be processed to find the unique workstations. Convert the workstation observation list into a set to remove duplicate entries. This leaves only unique resource identifiers, ensuring each station is counted once for accurate and efficient resource tracking. Adding a station identifier to a set ensures it is included among the unique stations. If CUT1 is already present, adding it again has no effect, because sets automatically ignore duplicates and keep only one copy of each element. We add the inspection station identifier INSP3 to the set of unique stations so it is tracked with the other distinct resources. Because a set prevents duplicates automatically, the identifier is only included once, even if it was already present. The check determines whether the resource identifier WELD2 appears in the set of unique stations. It uses a set membership test, and the resulting value is true if that resource was observed at least once among the scanned stations. Sorting the unique station identifiers alphabetically makes them easier to read without changing which identifiers are included. It simply creates an ordered list for clarity, which is especially helpful in a classroom setting. First, we print the total number of raw station scan observations. This count includes every recorded station entry, including duplicates, and shows the overall data volume before identifying unique records. This prints the number of unique station identifiers by counting the items in the set of stations. Because a set removes duplicates, the count represents the distinct resources observed, and the message explains what the number means. We display the unique station identifiers as a sorted list, so the results are clear and easy to read. This organized format makes the output more suitable for classroom discussion or presentation. The code checks whether the station identifier WELD2 appears among the unique observed stations. It saves the result as a true or false value, then prints a message reporting whether that station was seen. This script shows how sets manage unique workstation identifiers from repeated observations. A list with duplicates is converted into a set, so repeated identifiers do not change it, while a new identifier is added successfully. The script also checks whether weld 2 was observed, then reports the total observations, the number of unique identifiers, the sorted unique identifiers, and the membership result. Overall, it demonstrates that sets are useful for removing duplicates and checking membership efficiently. Set operations. Set operations help manage resource collections by focusing on what is included, rather than the order or number of repeats. They make it easier to compare and combine groups such as tools, machines, or suppliers. By treating these groups as sets, you can quickly identify what is available, missing, or overlapping, turning raw resource data into useful decisions. Set operations help answer practical resource questions quickly and accurately. By combining sets, finding shared items, comparing differences, or identifying exclusive membership, teams can unify resource lists, spot common tools, and reveal shortages without tedious manual checking. Set operations help analysts compare resource data from different sources. By focusing on unique items and avoiding confusion from duplicates or overlap. In engineering and operations, they can quickly show whether required training covers all chemicals or whether enough qualified operators are available. Overall, set operations support clearer, more informed decisions beyond their use in coding. Python code set operations. Sets help answer questions about unique resources by comparing what is required with what is available. In this example, the resources are maintenance tool sets. A required tools set stores the unique tools needed for a maintenance task, such as a torque wrench, caliper, safety glasses, and lift cart. Using a set prevents duplicate entries and makes it easier to manage and compare resources efficiently. The available tools set represents the tools currently in the storeroom, such as a caliper, safety glasses, a socket set, and a lift cart. Because it is a set, each tool appears only once, even if duplicates exist. This makes it easier to compare stored tools with the tools required for a maintenance task. Use a union operation to combine the required and available tool sets into one collection of unique tools. This removes duplicates and gives a complete list of every distinct tool involved in maintenance. Use the intersection operation to find which tools are both required for the maintenance task and available in the storeroom. The result shows the tools covered by the current inventory. Use set difference to find which required maintenance tools are missing from the storeroom. By subtracting the available tools from the required tools, you get only the tools that are needed but not currently in inventory. Use the symmetric difference operation to compare required tools with available tools. It returns the tools that appear in only one of the two sets, making it easy to spot what is missing or extra. This process compares required tools with available tools by showing each group in sorted order, then combining them to list all unique tools. It also identifies which required tools are already available, which ones are missing, and which tools appear in only one collection. This makes it easy to spot coverage and discrepancies. This script uses set operations to compare required maintenance tools with the tools currently available. It reports the combined list of unique tools, the tools that are both required and available, the required tools that are missing, and the tools found in only one set. The results are sorted to make the tool coverage and gaps easy to understand. Resource set comparisons. Resource set comparisons help teams quickly see how collections of machines, tools, or sensors relate. Because sets keep only unique items, they are useful for questions about whether something is present, not how often it appears. Comparing groups, such as machines due for maintenance and those sending alerts, can reveal urgent issues and reduce errors from manually checking long lists. Resource set comparisons help identify what is shared, missing, or unique across collections. They can show whether tools are available for a manufacturing task, which warehouse orders are ready to ship, or whether lab sensors are failing to report data. By turning raw comparisons into clear findings, they support faster and better decision-making. Set comparisons help engineering teams find mismatches between records and reduce compliance risk. By checking membership and overlap across areas such as safety, asset management, procurement, and training, engineers can spot gaps and confirm requirements are met. This turns complex coordination problems into clear decisions about what is included, missing, or shared. Python code, resource set comparisons. Use Python sets to compare collections of resource identifiers. Because a set keeps each identifier only once, set differences make it easy to find resources that are missing from one collection or extra in another. Define the required tools for an assembly cell as a set of unique tool identifiers, such as a torque wrench, fixture A, a caliper, and a barcode scanner. Because a set stores each item only once, it makes tool lists easier to manage and compare. A Python set is used to record the tools currently at the workstation, such as fixture A, a caliper, and a spare bit. Because sets automatically remove duplicates, the repeated caliper entry is stored only once. This keeps each tool unique, which makes later comparisons with other tool sets easier. Use set intersection to find which required tools are also available at the workstation. The common items form the ready tools set, showing which necessary tools are already on hand and supporting efficient resource management. To find missing workstation tools, compare the required tools with the tools currently available. The difference shows which needed items are absent, helping identify what must be added so the workstation is fully equipped. To find unexpected tools at a workstation, compare the available tools with the required tools and identify what is available but not needed. These extra tools can then be removed, helping keep the workspace organized, efficient, and limited to only what is necessary. To check whether the workstation is ready, compare its missing tools list with an empty set. If no tools are missing, the readiness value is true, meaning all required tools are available. If any tools are missing, the value is false. The process compares the workstation's required tools with the tools currently available. It first shows each set in a unique alphabetized form, then identifies which required tools are ready to use, which are missing, and which available tools are unnecessary. Finally, it reports whether the workstation is fully prepared by checking that no required tools are missing. This script uses Python sets to compare the tools a workstation needs with the tools it actually has, while automatically removing duplicates. It finds which tools are ready, which required tools are missing, and which extra tools are present. It then reports the sorted results and checks whether the workstation is fully prepared by confirming that no required tools are missing. Combined data records. Nested data records. Nested data records help organize complex industrial engineering information by grouping related details inside a single structured description. For example, a machine record can include its identity, location, status, history, sensor data, and operators, with smaller records for performance or maintenance. This keeps data readable and supports realistic planning and decision-making. Nested records help organize data sets where different items have related details inside them. For example, equipment data can include readings and supplier information, while warehouse data can include inventory and environmental limits. This structure keeps connected information together, making the relationships between parts of the data easier to understand without flattening everything into separate fields. When building nested data records, prioritize clarity, consistency, and simple organization. Each layer should group related information in a predictable place, such as inspection results and maintenance dates for a machine. Using dictionaries, lists, and sets thoughtfully helps represent engineering resources and their relationships in a way that supports analysis and decision-making. Python code, nested data records. Nested records help organize related engineering details in a structured way. Dictionaries can also hold collections such as lists and sets, making them flexible for representing complex data. Keeping records small supports clearer operational reasoning. A dictionary is created to store basic information about a piece of equipment. It records the equipment's unique asset identifier and its location on line A, making these details easy to manage and access in a structured way. A new operating section is added to the press record dictionary to organize equipment details. It stores the equipment status as running and the cycle time as 42 seconds, making these operational details easy to access. A supplier entry is added to the equipment record as a nested dictionary. It stores the supplier company as Metro Hydraulics and the region as Midwest, keeping these details organized within the main record. This code stores several Celsius temperature readings in a list within a dictionary. Keeping the repeated measurements together makes it easier to calculate averages or examine trends over time, which is useful for simple time series data. This code assigns a unique set of approved operators to the press record, including Amina, Luis, and Chen. Using a set prevents duplicate names and helps keep the authorization list clear for safety and compliance. A new dictionary is created to represent a second equipment record for a conveyor. It includes a unique asset identifier, conv008, and a location, line B. This makes it easier to manage and compare multiple equipment records. This assigns a set of approved operators to the conveyor record, including Luis, Maya, and Chen. It tracks who is authorized to use the equipment, and the set ensures each operator name appears only once. To find which operators can work on both the press and the conveyor, compare the approved operator groups for each piece of equipment and keep only the names that appear in both. This intersection identifies shared qualified personnel across the two machines. The press record provides two key details: the asset identifier, which uniquely identifies the equipment, and the operating status, which shows whether it is currently running. These values are extracted from the record and saved for later use or display. To find the average temperature, add together all temperature readings in the press record, then divide by the number of readings. The result is one summary value that represents the typical recorded equipment temperature. The output gives a concise summary of an equipment record. It shows the asset identifier, operating status, and supplier company name, then reports the average temperature, rounded to one decimal place. It also lists the operators shared by the press and conveyor records in alphabetical order. This script shows how to organize manufacturing equipment data using nested records. It stores details for a press and a conveyor, including asset information, operators, status, supplier data, and temperature readings. It then extracts useful results such as the press status, supplier company, average temperature, and operators shared by both machines. Overall, it demonstrates efficient handling of complex structured data. Linked data records. Linked data records help manage small industrial datasets by giving each item, such as a pump or sensor, a unique identifier. Other records can then refer to those identifiers to show relationships, instead of repeating the same information. This keeps engineering data compact, consistent, and easier to connect across different logs and databases. Linked data records reduce repetition by storing shared details once and referencing them when needed. For example, a maintenance record can point to a compressor while focusing only on service dates, technicians, and work performed. Using dictionaries and sets helps represent relationships such as repeated inspections or parts used across equipment, making small data sets more realistic while staying easy to manage. Linked data records work best when identifiers are clear, consistent, and stable, since mismatched names can break connections between records. Each record should contain only its own essential details, while related information such as location should be linked to the appropriate separate record. In industrial settings, this helps connect tools, materials, quality checks, inspections, and assets in an organized way. With well-chosen identifiers, even small datasets can represent complex networks and remain easy to update. Python code, linked data records. Linked records make industrial information easier to connect and understand. Shared identifiers reduce repeated engineering details, while sets support comparison across related resource collections. A dictionary named equipment stores information about each piece of equipment using a stable, unique identifier, such as pump 01, motor 17, or sens 03. Each entry contains a nested set of attributes, such as its area and either power rating or measurement range. This structure makes it easy to organize and look up detailed equipment records by identifier. A work orders dictionary maps each unique work order ID to its details. Each work order entry stores the related asset identifier and the assigned technician, making it easy to look up and manage work orders by connecting them to specific equipment and people. To find inconsistencies, compare the assets listed in work orders with the assets registered in the equipment records. Build one set from the equipment identifiers and another from the asset identifiers used in work orders. Any assigned asset that is not in the registered set represents a missing equipment record. Use an empty dictionary to count how many work orders belong to each asset. As each work order is processed, get its asset identifier and increase that asset's count, starting from 0 if it has not appeared before. The result is a tally of total work orders for every asset. The code compares registered equipment assets with assets referenced in work orders. It prints both sets of asset identifiers in sorted order, then reports any assigned assets that are missing from the equipment records. This helps quickly identify discrepancies where a work order points to an unregistered asset. The process reviews each asset in sorted order, matches it to its area using the equipment information, and reports how many work orders are tied to that asset. This creates a concise summary of each piece of equipment, its location, and its related work order count. This script uses Python dictionaries and sets to connect equipment records with work orders by their identifiers. It compares registered equipment with the identifiers used in work orders to find missing records, then counts how many work orders are linked to each asset. The output summarizes registered and assigned assets, flags any missing equipment, and reports work order counts along with each asset's area. Structured dataset records. Structured dataset records use built-in data structures to group related information into clear, consistent units. For example, each industrial asset can be represented with its identifier, location, and inspection date in one record. This makes the data easier to read, update, analyze, and share across programs or workflows. When building structured dataset records, prioritize consistency over complexity. Use the same pattern across records, with named fields for key details, sequences for ordered information, and unique collections to avoid duplicates. Whether tracking shipments or bridge inspections, this structure keeps each record clear, comparable, and easy for both people and programs to interpret. Structured datasets turn raw industrial data into information that supports better engineering decisions. Clear field names and consistent storage make data easier to check, analyze, and expand, even without complex databases. By choosing simple structures for attributes, sequences, and unique items, small datasets can still reveal issues such as overdue inspections, safety patterns, or energy service needs. Python code, structured dataset records. Structured records can combine built-in data structures. Dictionaries label the fields in each engineering record, while sets store repeated categories only once. We create a small maintenance dataset where each record describes an engineering asset. A record includes key details such as the asset ID, its location, and its current status. For example, asset P101 in the north pump room marked as running. This structure makes asset information easy to organize and access. The asset record summarizes key maintenance details. The last inspection was on May 20th, 2026, and Amina was the technician responsible. It also notes current faults, including a seal leak and vibration, and identifies the needed repair parts, a gasket and a bearing, to support follow-up, planning, and inventory management. This code defines a maintenance record for asset P10102 in the north pump room. The record shows the asset is currently stopped and notes that its last inspection was on May 12, 2026. This record shows that Diego was the last technician to work on the asset. Its fault flags use a set to track unique issues, such as vibration and a missing guard, while the required parts are stored in an array that includes needed maintenance components like a guard and a bearing. This code creates one maintenance record for an asset using a structured dictionary. It identifies asset C201 in the compressor bay, shows that it is currently running, and records its last inspection date as May 18, 2026. This format makes the asset information easy to access and manage in the dataset. The setup assigns Amina as the technician responsible for the asset, starts with no recorded fault flags, and identifies a filter as the needed maintenance part. Together, these details organize the task by showing who is responsible, what issues exist, and what part is required. A required field set defines the key information every dataset record must include, such as asset details, location, status, inspection date, assigned technician, fault indicators, and needed parts. It is used to check that each record is complete and follows the expected structure. We use a list comprehension to keep only records that contain every required field. For each record, we check whether the required fields are all present among its keys. Records that pass this check are kept as valid records, helping ensure the dataset has a complete and consistent structure. To collect all unique fault flags from valid records, combine the fault flag sets into one set. Using the union method removes duplicates automatically, so each flag appears only once, even if it occurs in several records. Unpacking the record flag sets lets the method merge them all at once, producing a single set of every distinct fault flag. To find all distinct parts needed across the valid records, create a set to store unique values. For each record, treat its parts list as a set, so duplicates within that record are ignored. Then combine these sets using the union method, gathering every unique part into one complete set for the dataset. We build a list of identifiers for equipment that is currently stopped by scanning the valid records and selecting only those with a stopped status. For each matching record, the asset identifier is collected. This gives a focused list of non-running assets that may need attention. This output summarizes the cleaned records by first showing how many valid structured records were found. It then lists the distinct fault flags and required parts, with duplicates removed and values sorted for clarity. It also identifies which assets are stopped and shows the technician name from the first valid record. The script reviews a small set of engineering maintenance records by keeping only complete entries. It then summarizes the valid records by finding unique fault flags and required parts, identifying any assets that are stopped, and reporting the technician from the first record. The final output gives a compact view of asset status, maintenance needs, and record completeness. In this lecture, you learned to build dictionaries that associate engineering identifiers with relevant values. Use sets to identify unique items and compare collections of resources. And combine built-in structures to represent small industrial engineering datasets. In the next module, Module 3, we will go over none.
Thank you for your attention. See you all in the next lecture.